talk about these. Both of these should have been pretty quick. Even though that last one, you might have drawn it out. It's very similar to one of the ones that we looked at yesterday. We looked at that same linear function over a very similar interval yesterday. But that first one right there, what does that definite integral evaluate to? Hardin, what'd you say?
I put 0.
It is 0. And why did you say 0, Hardin?
Because it's from pi to pi.
That's from pi to pi. We're looking for an area that has a width of 0. There is no second dimension to it. There is no area right there. We're going from pi to pi. And so even though you might have first looked at it and been like, oh gosh, sine of x, how am I supposed to do that? You realize, oh, it's from pi to pi. There we go, making it nice and easy. The second one, we have that x plus 2, so you can graph it, you can think about the area under this curve for sure. But the trick to this one is that the bounds are in the opposite position than what we would expect. And we talked about this super briefly at the very end of class yesterday, so if you don't quite remember it, then I understand. But we expect boundaries, our bounds of our definite integral, to go from A to B, from least to greatest. So because we have the 3 on the bottom, and it's from 3 to 0, this is going to be the same thing as a negative definite integral from 0 to 3. So if we find the definite integral from 0 to 3, the area under our curve, under our function, bound by the x-axis in 0 and 3, we get 10.5, and so this is a negative 10.5 on that. So the bounds do matter, the order of the bounds do matter. When we're thinking about directly area under our curve, we want our bounds to be from least to greatest. If they give it to you where they're from greatest to least, you can flip it, and when you do flip it, it applies a negative to it. We're probably going to see a few reasons why that is, kind of through some different examples and things as we kind of proceed through this lesson. And so, but essentially, we know we typically read from left to right when we read a graph. So if we're reading from right to left, it does switch it. That's a very quick way of explaining it. Like I said, we'll kind of see why that has to be true through some examples kind of throughout this lesson. But questions about either of these two? Any questions at all? All right. Yesterday was pretty crazy. We've had a kind of bizarro week. So we're going to kind of, again, slowly get into what we've been talking about with definite integrals. I'll do a little bit of a review of yesterday. We'll look at some new stuff for sure. But what I was saying yesterday at the beginning of class was that this really is the building blocks of a lot of what we're going to do for the rest of the year. This is also setting up what is super important to us, the fundamental theorem of calculus. This is not the fundamental theorem of calculus. The fundamental theorem of calculus does apply to definite integrals. It also applies to derivatives. It is the fundamental theorem of calculus. And all this stuff we're talking about, the stuff we're talking about literally right here, along with what we're leading to, the fundamental theorem of calculus, this is probably going to be 20% of your AP exam. Just the stuff we're talking about, essentially between now and winter break, or in December. That between here and the midterms, we are hitting such a significant part of your AP exam, and this will carry over, these ideas carry over into other parts of your AP exam as well. So it is super important to us. But we have kind of skipped out on this the last couple of days because of all kinds of crazy things going on. I'm supposed to continue talking to you about my college experience and things, okay? So some questions that we missed earlier this week. I usually have them on my phone, but it's back there, so here we go. My college application process. I applied to 3 colleges. I applied to UGA, I applied to GCSU, I applied to Macon State. Those are the 3 colleges I applied to. I did get into all three, but I ultimately chose Macon State. You're probably thinking, why? Why would you do that? My dad really influenced me to take the most financially secure route going into college. He wouldn't let me take out a loan. He didn't have any money to help me out, and Macon State essentially offered me the most money on top of the Hope Scholarship as it was, so that I didn't have to worry about paying for rent, didn't have to worry about food, anything like that. It was essentially just, it's like I was, sometimes scholarships feel like you're getting paid just to go to school. So that was the reason why I chose Macon State. I would have had to take out loans if I went to some of those other places. And there's something about, all right, Macon State, it'll be fine. And it was a pretty good time. Most of my college experience was spent around Mercer anyways, because, if you're in Macon, most of the young people that are at college age actually go to Mercer, because a lot of the people that went to Macon State were like 40 years old. And so, I did have some friends that were, I had two other friends that were also math education majors at Macon State, and we became really good friends until we graduated. We don't really talk anymore, but that's life. But most of my friends went to Mercer. I was involved throughout college in something called Young Life. I was a Young Life leader in Macon, and a lot of Mercer students did that as well. And so I had a community of friends at Mercer. I ended up living with a bunch of guys that went to Mercer down there by Tatnall Square Park and stuff. So it was a good time. I still had like a college experience. Still got to, move out of my house and stuff. It was just still in Macon. So it was fun. It was a good time. And my classes, it's one story I've kind of told to a lot of classes over the last couple of days. I obviously took a lot of math classes. I was a math major, and I also got education certification, but mainly I just took math classes. Math. I took like 13 or something math courses for my degree. And what is so interesting, I don't think other subjects were quite like this, is most of these classes, you had 4 grades for the semester. You had a test, you had a midterm, you had another test, you had a final. 4 grades. Did they assign homework? Sure, but you don't have to do it. It's kind of like our test reviews. It's like, just, keep up. Here's some homework to do, but they're not necessarily going to take it up. At the end of the semester, you've taken 4 tests. They drop the lowest test, and so 3 grades determine your grade in the class. It was a wild time. And because a lot of classes were like that, mid-September, here's the first test, and you'd have multiple classes with that first test all in the same week. It becomes really important also, because you only have a couple grades in the class. So that was pretty nuts. I kind of like that though, because you kind of show up for the test, you do your best, and it really affected your grade. So it worked for me, but it was a pretty scary thing as well. Also, relationship with professors and stuff like that. For the most part, I don't think they really knew who I was or knew my name or things. It's kind of the college experience. They know you as a name on a paper, and you turn your paper in, they grade it, and it gets back to you. But towards the end of college, when you're a junior, senior, you're really taking specific classes for your major. That's when you actually have classes that might be a lot smaller. Not too many people at Macon State were taking graph theory or number theory or something like that. And that's when you start building relationships with professors, and they know your name, and you can talk to them about life and stuff like that. But I think, I think a lot more teachers in high school knew who I was. So there's a couple things about college. Any questions for me? It was like 3 days worth of questions all rolled into one.
Did you meet your wife in college?
So one of my college roommates went to high school with her. He went to Northside in Warner Robins, and went to Mercer. I lived with him for 2 years or something like that, and we were going skydiving one weekend, and it was back there used to be this thing called Groupon. I don't know if Groupon's still a thing. Have you ever heard of Groupon? You get on the app and you're like, "Ooh, what deals can I get?" or whatever, and it's like, "Go skydiving for $50 or something like that." And so like we're all like, "Hey, jump on this Groupon." And he was the kind of guy who would always be like, anytime he would do something, he would invite like everyone he knows. So like he invited like all his friends from high school, like all his friends. So like we just had this crazy group going skydiving, and I guess she was home for the weekend. She went to college in Alabama, and she went skydiving with us. But we didn't start dating until we were like years later, because she was living in Alabama. That was, you know. But that's how we met, and then she went and like taught overseas and stuff. And when she came back, so like she went and taught in Indonesia for a semester, taught in Kabul for a semester as well, and then she was home for Christmas, and the Taliban directly threatened her school, and so the school closed and she didn't go back. And that's how we started dating. So, you know, quick. It's true. It's all very true. Yeah. And when she came back for holidays or whatever, that same friend was like, "Hey, I'm going to trivia night tonight. Everybody should come." So I went, and that's how we reconnected. Because he just invites everybody to everything. True story. All right, college.
Thank God for the Taliban, I guess.
You know what? For as much as the Taliban has negatively impacted a lot, I guess they positively impacted a lot. We'll edit that out of the video. I do not like that. I am completely. Yeah.
How was skydiving?
It was a blast. I recommend it. Shoot the skydiving. Find yourself a Groupon. It's a good deal.
Either way.
Yeah. There's that place over in like Thomasville. Not Thomasville. It was over there to the west of where we are now. Skydive Atlanta, I think is what it is. 855 dive or something. All right. Anyways, any other questions from the college? All right. Cool. So, yesterday we were starting to talk about definite integrals. Let's just get a quick overview one more time of our predicament, okay? Because what we have just seen so far, what we've seen are good situations where we don't need anything special. We really don't need calculus to answer this calculus question, because when we're looking for the definite integral of a function, we are looking for the area bound between the function, the lower and upper x values, and the x-axis itself. And unlike the ones that we've seen so far, most functions aren't that great. Most functions, if we're looking from A to B, we know most functions we're not going to be able to calculate this area with the geometric formula. This is not a shape that we ever dealt with in geometry. It's not a shape that you could really reason through. And so what we've looked at so far are those good situations. And sometimes, you know, like even if it was this crazy function, if we were going from A to A, that's a very specific situation where we can use some properties to get around that. One of the other things that we talked about yesterday is if a function goes below the x-axis. And if we're talking about our definite integral from A to B, and let's say that B is right here. We are going to have some area above that x-axis, and we're going to have some area below that x-axis. And the area above the x-axis is going to be considered positive. That area below the x-axis is going to be considered negative. And if we know that point where it crosses the x-axis, I'll let it be C, what we could do is we could take the area above that x-axis which would be the definite integral from a to c, and we can add it to the area below the x-axis. The pieces will add up to be the whole. And if we knew what these were, maybe this one right here is a positive 1, 2, 3, 4. Let's say it's 5. It's probably not really 5, but it's close to 5. We'll say this one's a negative 1, 2, 3, 4. We'll say this one's a negative 13. That would mean we have this definite integral evaluates to be positive 5. This one evaluates to be a negative 13. And so ultimately, this definite integral from a to b would evaluate to be negative 8. So the area on top can kind of essentially cancel out with the area on the bottom to give us our definite integrals evaluation. So again, we kind of talked about this yesterday, but it's a little bit calmer today. It's really important to just kind of understand the concept of what we're looking with, and understanding that ultimately, if I didn't tell you that was 5, right now you don't have the ability to find exactly what that is. And that's really the problem that we're working around until we get to our fundamental theorem of calculus. That'll solve that problem for us. All right, let's talk a little bit more here. Let's add to what we know. So here's those properties we talked about yesterday. You just use them on the warm-up. If our lower and upper bounds are the same, we get to 0. If we want to flip our bounds, because typically we want to go from least to greatest, and if it's not written like that, you can flip it to make overall, it's going to change the sign of our definite integral. So the next property is one that we have we just used this. I just used this and everybody nodded along like it made sense, so that's good. If we want to find the definite integral from a to b, and c is some other value, then this is going to be the same thing as the definite integral from a to c plus the definite integral from c to d. I think I just wrote that with literally the exact same letters, not even intending to. To draw up that same function we just looked at. This was a great use of that additive interval. We wanted to find the definite interval from a to b, so we took from a to c, we added it from c to b, and this is often very helpful because we might not be able to look at the whole definite interval at once. We might have to break it down to be smaller pieces. Here is just a quick usage of it. We're looking at the absolute value of x. The absolute value of x is one of those parent functions that you know a lot about, so this isn't too crazy to get that graph real quick. And if we wanted to go and find that area from -1 to +1, what they're saying is that, hey, you could break this down to be the definite integral from -1 to 0 of the absolute value of x dx, and then add that to the definite integral from 0 to 1 of the absolute value of x dx. And so we could find these two areas individually. This one right here would be a +1/2. We could find this area right here from 0 to 1. It would also be a +1/2. And if we add up those two, we get 1. So hopefully that's just confirming what you would want. The parts are adding up to be the whole. Questions about that? Here's two more properties that they're really the same kind of properties we've seen when it comes to everything in this class so far. Limits, derivatives, indefinite integrals. Here it's applying to definite integrals as well. So these properties should be very familiar to us. If we have a constant times our function, we can factor that out. So if we had from a to b, if we had 2f of x, then we could factor out the 2. We could find the definite integral from a to b of f of x dx and then multiply it times 2. We've been able to do that with, again, limits, derivatives, indefinite integrals. And the second one here says that we can look at each term individually as well. If we have, and again, it's shown as two functions, but it could be like we're looking at the definite integral of x squared plus 3x, and you want to look at each of those individually. Well, we could do that. We could evaluate the definite integral of the first term and add it to the definite integral of the second term. Again, you've applied that for everything throughout this class, and it's just nice to know that it also works for definite. We're going to look at an example together, and then I'm going to let you try a bunch of this stuff. So let's take a look at this one together. We want to evaluate this definite integral. This is our goal. And they give us some bits of information. They give us the definite integral from 1 to 3 of x squared, from 1 to 3 of x, from 1 to 3 of dx. And remember, we know there's an understood 1 in front of that dx right there. Can we all close the door?
I'm good.
Very distracting. To me, probably not. All right, so I'm going to apply a bunch of properties, mainly the ones we just saw on the previous slide, to break down this definite integral. I'm first going to look at that first term. And I can rewrite this as the definite integral of 1 to 3 of x squared dx, and just pull out that negative. That leading coefficient is a -1, so I can just pull that out, and I can rewrite that as the definite integral of x squared dx, looking specifically at that first term. For that second term, I can pull out the 4, and I can go from 1 to 3 of x dx. And that final term, I can pull out a -3 and be left with the definite integral from 1 to 3 of just that dx. So remember, that's an understood 1, and 1 times -3 would get us that -3 again. It is important to see the notation. The College Board sees notation on your test as is like them being able to see how much you understand, and it's their way of glimpsing into your brain. And so if we were breaking this down, if you needed to use this technique on the AP exam, for instance, you would want to make sure you're including that dx in all three of these terms. Because every time, essentially, the integration symbol and the dx are like they go together. We can't integrate without to know what variable we're integrating with respect to. So if you're writing this integral symbol, we also are going to include our dx, or maybe the variable's different. You know, if we had a y right here, we would have dy. But whatever the variable is, we want to make sure we include that dx. That is really important. You don't want to undersell that. From there, though, we do know the definite integral from 1 to 3 of x squared. It is 26 over 3. And they gave it that. I know you don't know what that is, but they gave us that as part of the problem. They gave us that as 26 over 3. So I have a negative 26 over 3. Here, the definite integral from 1 to 3 of x is 4, so we have a plus 4 times 4. And then finally, the definite integral from 1 to 3 of dx is 2, so I have a minus 3 times 2. And now we just finish up the problem. Negative 26 over 3. This is 16, and I'm going to, this is probably wasting our time a little bit, but I'm going to common denominator. 16 times 3 is 48 over 3, and this is 6. 6 times 3 is 18 over 3. So I'm just combining into one. Negative 26 over 3 plus 48 over 3 is a positive 22 over 3 minus 18 over 3 gives us a negative, positive 4 over 3. So unless I made some egregious mistake throughout here, that should be it. But the calculus stopped right here. At this point, I was just working through combining those terms. If you see how we broke down those in those individual terms, we use those properties of our definite integral, we evaluate those definite integrals using what they gave us. After that, we're just simplifying. All right. Thoughts, questions on anything here? All right, take a look at these. We have 3 questions, very similar to the one we just looked at. They did give us 3 pieces of information we can use, and we are trying to evaluate these definite intervals down here. So think about what you're trying to find. Think about all the properties we've learned. How can we find the solutions to these definite intervals? Alright, so that first one, even though they gave us a bunch of stuff from 2 to 6, from 2 to 6, from 2 to 6, here it's from 2 to 2! We do want to be on the lookout for that because you know if the bounds are the same, you know it's going to come out to be 0. They're just trying to trick you a little bit on that one. But the next two are pretty much exactly what we were looking at from the previous example. I rewrote this by pulling out the -3, and I know I can find that definite interval using the property they gave, or the fact they gave me there in my problem. In this last one, I broke down each term individually. You can see how I broke it down, how I plugged in what they gave me, and I got a -316. Any thoughts, questions about these three here and the properties? All right. Finally, I'd like you to take a look at these two right here. This one right here, this is going to be, this will probably and potentially, there we go. This is potentially going to take you the rest of the period, and that's fine. Whatever we don't finish today, we will finish as our warm-up tomorrow, so that is fine. It's not the end of the world. But we are looking at these intervals, and we can calculate the definite interval with our geometric shapes right here. So you might have to apply some of your properties, your additive interval, to look at those shapes, add them together. Remember, underneath the x-axis is going to be negative areas, above the x-axis will be positive areas, and so on. But they always give problems like this on the AP exam. Sometimes they're very straightforward like this, sometimes they have different little context to them, but being able to evaluate definite intervals with our geometric shapes, with a graph, definitely directly related to our AP exam for sure. So apply properties when you need to, because notice when there's a coefficient to your f of x, and f of x is what's graphed right there. If you finish that one, you can go ahead and start looking at this problem here. Like I said, I'll kind of be coming behind you if you want to talk about things or recheck things. I'm happy to. Whenever we don't finish today, we will probably finish as our warm-up tomorrow.